learn more about the properties of charges, let's observe this diagram of an atom. Inside the nucleus, there are protons and neutrons. These never leave the nucleus. And outside, in the electron cloud, there are electrons, which can be transferred from one atom to another. There are two kinds of electric charges, positive and negative. The protons have positive charges, while the electrons have negative charges. Here, you will see a person rubbing a balloon against her hair. The balloon and her hair do not have the same charges, so they become charged and attract each other. Now, here, you'll see two balloons with the same charge, so they repel each other. In short, like charges repel and unlike charges attract. And finally, electric charge is conserved, meaning in a system, electric charge can neither be created nor destroyed. Take the balloon against hair example again. When the balloon is rubbed against your hair, some of the hair's electrons are transferred to the balloon. This way, the balloon becomes negative and the hair becomes positive. Here, you will see a picture of Robert Millikan's oil drop experiment. The oil droplets were charged in the atomizer and passed through the hole in the top plate. First, the droplets all fell. Then, he charged the top plate with a positive charge. This caused the droplets that had a negative charge to be attracted to the positively charged plate. Millikan repeated this for many drops, and once he was done, he found that there is a fundamental unit of charge, which is represented by the letter E. Basically, the charge is quantized, meaning an object has a charge that occurs as integer multiples of E. Induction is the process of charging a conductor by bringing it near another charged object and grounding the conductor. Let's look at this picture here to understand this concept. A negatively charged rubber rod is brought closer to a neutral metal sphere which is insulated. Now, the electrons in the rubber rod and the electrons in the sphere will repel each other, so there is a redistribution of charges in the sphere. Then, if a grounded conducting wire is connected to the sphere, some of the electrons will go to the earth through the wire. This will leave the sphere with more positive charges than negative. Still, the electrons in the sphere and the ones in the rubber rod repel each other. Lastly, if the rubber rod was removed, the charges would redistribute themselves because there is no repulsion anymore. However, there are still more positive charges in the sphere than negative. Polarization is what causes a surface charge to be induced on insulators. When a charged object is brought near an insulator, there's a realignment of charges which causes more positive charges on one side than the other. When this occurs, the object becomes polarized and it is able to attract or repel other objects. However, it still is neutral and has no net charge. For example, in this picture, the balloon is attracted to the wood because the wood molecules have become polarized.
Coulomb's law states the magnitude of the electric force between two-point electric charges is directly proportional to the product of the two magnitudes of each charge and inversely proportional to the square of the distance between the charges. In other words, F equals K times Q1 times Q2 divided by D2. The F is equal to the amount of electric force. The K, being the Coulomb constant, is always equal to 8.99 times 10 to the 9th power. Each Q stands for one of the charges, charge 1 and charge 2. D means the distance squared in the equation. For example, if both charges were equal to 1.60 times 10 to the negative 19th and the distance was 5.3 times 10 to the negative 11th, what would the electric force equal? Let's plug in the numbers to our standard equation.
An electric field is a region where an electric force on a test charge can be detected. To find the strength of the electric field, you must look to the diagram of an electric field and pay particular attention to the field lines. The number of field lines is proportional to the electric field strength. For example, 6 field lines represent 1 coulomb. Therefore, this diagram had a magnitude of 1 coulomb. If there were 12 field lines, then the charge would have a magnitude of 2 coulombs. Notice that the lines are directed outward. This tells us that the diagram is for a proton representing a positive charge. If they were directed inwards, the diagram would be for an electron representing a negative charge.